Number Theoretic Functions Part 4, the Mobius inversion formula. Welcome back. We are now ready to start talking about the Mobius function. It has the following definition. Mu of n equals 1 if n equals 1, equals 0 if p squared divides n for some p, and equals minus 1 to the power r for n equals p1, p2, p3 all the way up to pr. So the first operation carried out by the Mobius function is to sieve out those numbers that are not square free. Out of those that remain, the function yields 1 if it is the product of an even number of primes and minus 1 if it is the product of an odd number of primes. Notice how 1 is the product of no primes, hence it is convenient that the function states that mu of 1 equals 1, because minus 1 to the power 0 equals 1. With this in mind, we now venture to prove that the Mobius function is multiplicative. We first realize that if the GCD of Mn equals 1 and p squared divides m or p squared divides n, then p squared divides mn. In this case, 1 of mu of m or mu of n is 0 and mu of mn is certainly 0. Therefore, mu of mn equals mu of m into mu of n. So to make further progress, we consider what happens when both m and n are square free. Let m be the product of r distinct primes and n the product of s distinct primes. M and n do not share any prime factors. Therefore, the number mn is the product of r plus s distinct primes, and so mu of mn equals minus 1 to the power r plus s. Mu of m equals minus 1 to the power r and mu of n equals minus 1 to the power s. Again, we see that mu of mn equals mu of m into mu of n. This proves that mu is multiplicative. The next step, which takes inspiration from the groundwork laid down in part 3, is a key step in leading up to the Mobius inversion formula. We define the function capital F to be the sum of the Mobius function over the divisors of n. Capital F of n equals the sum of mu of d over the divisors of n. This function capital F is also multiplicative, as was shown in the previous part, since the multiplicativity of mu induces multiplicativity in capital F. Knowing this, we come to the realization that in order to evaluate the value of f for any n, all we need to determine is its value at powers of primes, since all primes are co-prime, and we can then leverage the multiplicativity of f in conjunction with the prime factorization of n in canonical form to calculate capital F of n. So capital F of p to the k equals the sum of mu of d over the divisors of p to the k. But there are precisely k plus 1 divisors of p to the k. These are 1, p, p squared all the way up to p to the k. Calculating, capital F of p to the k equals mu of 1 plus mu of p plus mu of p squared all the way up to mu of p to the k. But we also learnt from the definition of mu that whenever I is greater than or equal to 2, mu of p to the I equals 0, as it is no longer square free. Mu of p equals negative 1 because p is a product of only one prime factor, itself. Thus for all k greater than or equal to 1, capital F of p to the k equals mu of 1 plus mu of p, which equals 1 minus 1, which equals 0. The only case when f of p to the k equals 1 is when k equals 0. In other words, f of 1 equals 1. In fact, at this point, we can bring up the fact that any multiplicative function f that is not identically 0 must satisfy the criterion that f of 1 equals 1. This is because there should exist an n such that f of n is not equal to 0, and so f of n, which equals f of 1 into n, equals f of 1 into f of n, as 1 is co-prime to every other number. This reduces to f of 1 equals 1, as f of n is not equal to 0. With that detour complete, we now return to the main attraction, equipped with some key insights. For all n greater than 1, we can write n equals p1 to the k1, p2 to the k2 and so on, all the way up to pr to the kr, where all the exponents are non-zero. In this case, capital F of n equals capital F of p1 to the k1 multiplied by capital F of p2 to the k2 and so on, all the way up to capital F of pr to the kr, which equals the multiplication of a string of zeros, as all the exponents are non-zero, and capital F of p to the k equals 0 whenever k is greater than or equal to 1, or in other words, k is non-zero. The function we defined, capital F, is 0 everywhere except when n equals 1. This is an important fact that will come in use later. After a long wait, we reach the point where we can disclose the Mobius inversion formula and then follow it up with its proof. In the past, we studied functions defined as being the sum of other functions over the divisors of n. More accurately, we are talking about general functions capital F and little f defined such that capital F of n equals the sum of little f of d over the divisors of n. The Mobius inversion formula gives us a way of rearranging this formula to make little f the subject and define it in terms of capital F. Here is its statement. Little f of n equals the sum as d divides n of mu of d multiplied by capital F of n upon d, which equals the sum as d divides n of capital F of d multiplied by mu of n upon d. To save everyone the trouble, let me quickly mention that the two equations on the right are in fact identical. Since d divides n, we set d prime equal to n upon d, and as d runs through the divisors of n, so does d prime, but in the opposite direction. More precisely, the sum as d divides n of capital F of d multiplied by mu of n upon d equals the sum as d prime divides n of mu of d prime multiplied by capital F of n upon d prime. This is exactly the same formula, but only d replaced with d prime. As far as the proof is concerned, we start by using the definition of capital F and substituting it into the right hand side. We have that the RHS equals the sum as d divides n of mu of d into capital F of n upon d, which equals the sum as d divides n of mu of d multiplied by the sum as c divides n upon d of little f of c, which equals the sum as d divides n of the sum as c divides n upon d of mu of d multiplied by little f of c. Here we moved mu of d inside the second summand. This can be thought of as a series of sums. When d equals 1, we have the sum as c divides n of mu of 1 into f of c. When d equals n, we have the sum as c divides 1 of mu of n into f of c. In general, we have the sum as c divides n upon d of mu of d into f of c. Now each of these sums may or may not contain the term mu of d into f of k for the particular value of c equals k. We make an attempt to group all the terms containing an f of k together. Notice how every f of k is multiplied by a given mu of d only if k divides n upon d, whereupon the term mu of d into f of k appears in the sum as c divides n upon d of mu of d into f of c for a given value of d. Conversely, every mu of d such that d divides n upon k is multiplied with f of k. This is precisely the grouping we desired, and its virtue is that it allows us to regroup the series of sums in the following way. The term mu of d is multiplied and paired with f of k only if d divides n upon k, and so each term in the series now looks like the sum as d divides n upon k of mu of d into f of k for each c equals k. Hence we have succeeded in grouping terms by the f of k factor they contain. The entire sum is captured by allowing c to traverse all the valid numbers that it could in the original double sum of the sum as d divides n of the sum as c divides n upon d of mu of d into little f of c. Hence k is replaced with c, a general value, and we write that the double sum now equals the sum as c divides n of the sum as d divides n upon c of mu of d into little f of c. The reason c itself takes on the value of every divisor of n is simple. The conditions in the original sum were d divides n and c divides n upon d, but d equals 1 is a divisor of n, whereupon the constraint on c is just c divides n. It is in this case that c takes on the value of every divisor of n if it hasn't already before. Hereafter, we can factor the f of c out of the first summand, which only varies the d value while keeping c fixed. This gives that the RHS equals the sum as c divides n of little f of c multiplied by the sum as d divides n upon c of mu of d. But we saw that the sum of the Mobius function over the divisors of a number is 0 unless that number is 1 itself, in which case the sum is 1. Mathematically, the sum as d divides n of mu of d equals 0 for all n greater than 1. Hence, whenever c divides n and c is less than n, then the sum as d divides n upon c of mu of d equals 0 as n upon c is greater than 1. But if c equals n, then the sum as d divides 1 of mu of d equals 1, and when c equals n, little f takes on the value f of n. Therefore, f of n is the only surviving term on the right hand side, as all the rest cancel out. This means the RHS equals little f of n, which is equivalent to the left hand side, thus proving the formula. Now to clarify things, let us apply the Mobius inversion formula to the functions tau and sigma. We saw in part 3 that tau of n equals the sum of 1 as d divides n, and sigma of n equals the sum of d of the divisors of n. This gives that 1 equals the sum as d divides n of mu of d into tau of n upon d, and n equals the sum as d divides n of mu of d into sigma of n upon d. We will not have much occasion to make use of these formulae, but as individual facts, they are quite interesting as they apply for all n. With this, we end part 4. Join us in the next part where we consider a more important application of the Mobius inversion formula. namely to show that the converse of the theorem proved in part 3 is also true. More specifically, for functions F and f related by the equation F of n equals the sum of f of d over the divisors of n. If F is multiplicative, then so is f. The credit for the theory and the proofs goes to David M. Burton, who is the author of the book Elementary Number Theory. Credit is also given to McGraw-Hill Education India Private Limited, who have published the Indian edition.